Hello and welcome to the part 4 of creating your model manually with JSO. So this part is going to be very short. Essentially, I want to talk about creating a model that modifies another model. So the easiest one I came up with was regularization model. So this is inside JuliaSmoothOptimizers / regularization model.jl, which is a link inside the guidelines. So it's a very simple model which takes an existing constraint model and adds a regularization term of this form here. Half of rho times the norm of x minus z squared. So rho is inside our reg NLP, which is our structure for our model, and z as well. A big difference is that we don't have counters inside this model. Why? Because any evaluation of f for this model is going to be an evaluation of f for the internal model. So instead of keeping those evaluations, we keep the inner model and use those counters, okay? This could be wrong, for instance, if you want to use f and the regularization at the same time and have the counters be different, okay? So this could be wrong. But then again, if you want to use them at the same time, you should probably be worried about efficiency because you're going to be computing the gradient and Hessian twice, okay, one for each model. So you probably don't want to do that. So using only regularization model, this is correct. So meta, as I said, you always have to put a meta, NLP model meta here. Inner, which is a different thing, rho and z. So our constructor receives a model, an existing model, rho and z, and it says that the number of non-zeros in my Hessian, which is an important value that you have to pass, is gonna change. It's not gonna be just the Hessian anymore. It's gonna have n other terms, which are the terms from this. Okay, so if you compute the second derivative of this, you're gonna have Hessian of f plus rho times the identity. So rho times the identity are these n values. This is something for the counters, so I skipped this in our early tutorials. If you want to get the counters of a model, so for instance, I have NLP here, okay? So I have objective equals 1. If I want to get that value, I can call neval obj of NLP, and it will get that value. So since this model does not have counters, it has to redirect any call of this function to a call of the internal function. So for each counter in counters of the field names of counters, and in addition to some counters and reset, define this function called in this method to be the function called in the inner method, the inner model, this model, sorry. Same way, I have the increment of any symbol of this model to be the increment of the inner counter. Okay. These at the font inner counters should do this. At the time that I committed this, it was not released yet, but now it should be released. So you can just say at the font inner counters or some other names. I think it changed to the at the font counters. By the way, our guidelines should have something. At the font. Here. It changed to at the font counters. So you can just say at the font counters, your model that wraps another model, and the name of the internal model, the field of the internal model. So inner in our case. Okay. The objective function is gonna be the objective function of the inner model plus rho times the norm of x minus z squared over 2. The gradient, notice that I have gradient exclamation mark. Call the gradient exclamation mark at that point and add a new part to it that has structure. Use views to compute the structure at the first n z values, and the last values n values are just 1 to n. The has chord is the same thing. I have x val, same thing. And I use views to update the first n z values, and then I set the other values to be rho. H prod exclamation mark, same thing. I just update HV a little bit. So with this very simple modification, less than 70 lines, I now have a regularized model. This is a L2 regularization, something like a proximal model, like how do you say, around point Z. So very easily you can expand a model by creating a regularization on top of it, okay? This should not be much slower than the original model. In fact, we can copy this all the way to here. Paste. Is it pasted? It is pasted. I define extended Rosenblock with 100 values. Output IPOpt with a print level 0. Print the output. So it solved very quickly in 0.08 seconds. If I say that our NLP is the reg NLP of the extended Rosenblock, and it's gonna fail because I forgot to say around which point. So let's say it's 10 to the minus 2 around the point zeros. Extend, I forgot to close the parentheses here. Oh, this is interesting. Reg NLP has no field counters. Where is it? Oh yeah, because of the new way that I'm showing. So I have to update the show method as well. So yeah, this has to be updated. That's so cool. So I have a show IO. Not NLP models, it's base. Show IO for a reg NLP is gonna be, and I'm gonna copy here what select models does. So I have to do this. I'm gonna ignore show header and focus on show header, show NLP meta, and model counters. Show. By the way, is this the? Oh, this is not the last one. Let's hope I haven't changed it. NLP meta and NLP inner counters. Counter. Should be counters, no? So let's define show header. So show header is gonna be regularized model. And now our regularized model also prints very beautifully So I'm gonna have a regularized model, sorry, and this model has a show and has a base.show. So the number of non-zeros, it is how much was it? 3n/2, I think. So it was 150 plus 100 for the diagonal, 250. And here is IPOpt running this model. Let's run again, so it has the precompile effect. It took 0.009 seconds. So again, to compare, 0.007 and 0.004. Anyways, it's not much. Notice that the solution is not the same, of course, because this is a regularized model. So this is interesting because you could have something like a very a model with a solver with a very high tolerance. So here we have a model that works, so it's not a very interesting example, but you could have something like NLP is an extended Rosenbrock, or ADNLP model, for instance, is not a good model. Sum of x to the fourth, and I'm gonna use 10 values and constraints. I'm sorry, 10 variables. And I'm gonna say the reg NLP is a regularized NLP of this NLP using 1.0, and then thinking the current starting point. Okay, so I have this. I didn't need to show it. And I could have a method, something like output is with logger, no logger, do trunk NLP, reg NLP, starting from the point x with a tolerance of the gradient at x, relative tolerance actually, and then I will say that my regularized NLP is thinking. Well, my regularized NLP is gonna use the point x, which is the current point, and my regularized NLP is gonna use a smaller value. Is this gonna work? If it doesn't work, I'm just gonna delete and go back to what I was doing. It's norm of the gradient. Of course, you should have something a little bit more efficient. No, the norm of the relative tolerance shouldn't be the norm of the gradient. It should be a value tau. It should be the same row, for instance. Regularized NLP row should be 1. So I ran the first time, nothing worked because the tolerance was too high. I run again, and it's walking to the solution slowly but surely. Okay. So of course the relative tolerance is also going to 0. And Z is 0. Yeah, it was interesting to test this just for fun. Okay. So you could, instead of doing this, you could have a minimum value for the tolerance, something like this. Okay. Except now that the relative tolerance is not going to be so small anymore. So that's it for the part 4 of our video. So let me know if you want more information on how to create a model in some other way, some specific information about that. You can contact me on Twitter or GitHub by email I have on GitHub, or even by leaving a comment in the video on YouTube. Okay, I'm also on the Julia Slacks and anything like that. So thanks for watching, and please like and subscribe. Follow me on Twitch as well and on Twitter. I'll see you next time.